Whenever I'd come across quantum mechanics before, I would notice that almost any source that I was learning it from, whether it be some lecture notes or a book or through the media, I would notice that a lot of these sources presented the quantum mechanics from a viewpoint, through an interpretation, and that there was often very definite language used. I'd like to illustrate this with an example, namely the measurement problem. This problem talks about when you have a particle. Say that particle could be in many different positions, and we want to measure its position. Before we make the measurement, that particle could be in many different position states, and before you measure it, it exists in a superposition of all of these different possible position states. And that superposition is described by a thing called the wave function. Now, the wave function is this abstract, continuous function that somehow contains all the information about this particle. As an aside, I had many questions starting the project, and still do, about what the wave function really is and whether or not it has a physical interpretation to it. But anyway, the measurement problem then goes on to describe what happens when you make a measurement. So when you make a measurement, say you bounce a photon off the particle, you then know with quite high precision where its position is. And so the wave function now is a spike centred at that position. And so we have this problem of a continuous wave function now suddenly being this spike. This raises a whole load of questions, such as where was the particle before we made that measurement? Was it at that spike, or was it somewhere else? Also, is there any way that we can know where it was before the measurement was made? There are also questions about how exactly this wave function suddenly and instantaneously collapsed to a spike. That discontinuous jump is a bit of a problem. And also there are questions on what exactly is meant by a measurement. I detailed bouncing a photon off the particle, but there are many other ways in which you can make the measurement that also provide this seemingly wave function. A lot of sources that approached this often presented it and other quantum mechanics material from the Copenhagen interpretation point of view, and they used very definite language, kind of stuff like the wave function does collapse, and that there are no physical properties prior to making a measurement, and that the system is somehow changed when you make a measurement, such that you then get the properties out that you previously measured. I had also heard of other different interpretations. The other one that I'd mainly heard of was the many worlds interpretation, and I primarily heard of that through the media, as it was, as it's been quite popular in the media, as it is quite a, you could describe it as a very phantasmagorical kind of interpretation, because it details that whenever you've got loads of different possibilities, so you could measure a particle in spin up or spin down, all these different quantum possibilities are actually explored in the many worlds. It says you don't just have one. Every time there has to be a decision almost into what state to go into, the world actually splits off, the whole universe splits, and so splits into as many universes as it needs to explore every single possibility in reality. And it says that we are only in one, and we can only see one, and we can't see any of the others that happen. I'd also heard of other statements from other different interpretations, like the Feynman path integral. I'd heard of statements that particles could take bizarre trajectories that didn't seem to conform to normal physical laws, and that they were still possible. However, I hadn't looked very much into these, and I think my views before the project can really be summed up by actually this kind of almost subconscious bombardment that I'd taken on from different sources. And so I'd actually just kind of subconsciously absorbed, without as much questioning as I really needed to do, about primarily the Copenhagen interpretation. I think that a lot of the sources had really impressed upon me that things like the wave function does collapse, and so that was my kind of view before coming into the project and questioning a lot more. I would say that yes, my views have changed after the course of the project, because now I've had a little bit of time to look into some different interpretations and kind of what they mean. One interpretation I was really interested in was actually the de Broglie-Bohm interpretation, because it answered some of my questions about the wave function in a really bizarre way. The de Broglie-Bohm theory said that the wave function was actually a real field propagating in space, and it was coupled to the particle that it described. And it meant that quantum mechanics could then be formulated in an entirely deterministic way, because classical mechanics says that if you know all of the initial positions and the initial velocities of, say, particles in a gas, then you can know how that system's going to progress in time. However, with quantum mechanics, this seems to be different. We seem to only be able to predict the probabilities that we're going to get certain results when we make measurements. And the de Broglie-Bohm's pilot wave theory now brings in an entirely deterministic way of doing quantum mechanics. However, there's a problem with this, in the sense that this theory seems very, very complicated, certainly in the mathematics, and so a lot of physicists argue on the grounds of Occam's razor, saying that there are simpler explanations that give all the same answers in quantum mechanics, and so this theory is not actually going to be correct because it's too complicated. There's also the problem that it's a non-local theory. For example, if you have the double slit experiment and you're only letting electrons through one slit, the de Broglie-Bohm theory says that there's a force on the electrons as they go through one slit. And when you then open the second slit, there is an instantaneous change in the force. That's described as this kind of action at a distance, non-local problem, and that's seen as something that can't really happen in a theory that's going to work to describe quantum mechanics. Many-Worlds interpretation was an interesting way of getting around the measurement problem by saying that there was actually a universal wave function that described every one of these possible bubble universes, and so actually the wave function didn't need to collapse when each possibility was explored in the splitting of different universes. However, there was a problem, it seemed, in the whole energy conservation, this huge law that seemed to be kind of being broken by this answer to trying to solve the measurement problem. Another interpretation which really kind of had an impact in changing the way I thought about the wave function collapse was the ensemble interpretation, because this interpretation said that the problems with the wave function collapse came about when you tried to apply the wave function to a single particle. The ensemble interpretation says that the wave function actually applies to an ensemble of identically prepared theoretical systems that are the same. And so the wave function actually gives you the probabilities on that statistical ensemble on what results you're going to get when you make a measurement, and so actually there is no need for the wave function collapse in that interpretation. Another area of interpretation that I looked into that really changed and questioned my views on the double slit experiment was the Feynman's path integral formulation, because the Feynman's path integral formulation stated that say if it was with electrons in the double slit experiment, that those electrons travelled in really bizarre paths that were not classically thought of to happen, and each of those bizarre paths had a probability amplitude, a certain probability of actually happening, and when you summed those probability amplitudes, you actually got the prediction of the interference pattern on the screen, and so that really, really challenged my way of thinking about the double slit experiment. I would say that actually for me that's a really difficult question to answer, because now it's almost as if my previous views have been quite shaken. Previously I had been kind of almost subconsciously accepting of any kind of interpretation that had been kind of told to me, and in any way that quantum mechanics have been taught. And so now, after looking into some different interpretations, I feel like now I have even more questions, and that I feel that before I want to go and say that I think that the ensemble interpretation is the best way of thinking about things, or this, that and the other, I would say that actually I feel like I now need to go and research even more. I feel that I now need to go and try and answer my questions about all these different interpretations by looking more into the interpretations, looking more into also the formalism of quantum mechanics and kind of what's buried in there. So I would say that my views now are actually ones of, I have more questions now, and now I'm actually more intrigued and more interested to go and look at these questions and try and answer for myself what kind of interpretation I do think is the best way to describe the quantum mechanics that's going on. I would just like to say thank you very much for taking the time to look at our website. We hope it's been very interesting, and yes, so thank you very much.